Hello, everybody. Welcome to Geology. Let's talk rivers. We'll be working through most of what you see in chapter 14 of the text. And should you want to go along with the notes, they're available in the course in the segment. So we're going to start with drainage basins, which we should define. And I also will throw on there that these can be called two things. We can call it a watershed or a drainage basin. And I think your book says that right at the beginning too. Boom, boom. Section 14.2. And what it would refer to is the area of lands that all drains into one stream system. So I'll check that on there in case people want it. Area of land drained by a stream system. So I threw one on here for the drainage basins of New York, the major ones. You can kind of do these on smaller and smaller scales, right? But for the big ones, here's what we got. Let's look at the Oswego one since that's where most of us are. So this light blue one, all of that water enters the Oswego River. It's kind of interesting, I guess. The all of the Finger Lakes, all of these cities through here, if you want to talk other campuses like Ithaca and Cornell, all the water that hits that all washes up and goes to the Oswego River. But water from campus itself doesn't actually go into the Oswego River, just because we're so close to the lake. It all just goes right into the lake right there, right? So that's what these thin ones right along the lake would be. But the Oswego River has, again, all of the Finger Lakes all drain north, enter the Seneca River that heads over towards just north of Syracuse. Oneida Lake comes from over on this side, on the east side, and heads over to just north of Syracuse. And then up through Syracuse is Onondaga Creek. And all three of those meet just north of Onondaga Lake, right about here, and come up through the Oswego River. Color coded, it just makes it kind of easy to see. So keep in mind that it's an area of land. That's what it like. That's it. It's a physical geographical amount of space. Everywhere is part of a drainage basin. When water hits, it's going to drain somewhere. So it's worth considering, understanding that everything you do within these areas affects the water quality of that area. If you've ever seen signs, there's been one put up. If anybody comes up Route 81 from the south, right around Tully is where you'll see a big sign that says you're now entering the Lake Ontario watershed. Just to raise awareness. You'll see them around here too, smaller scale. There's signs saying you're now entering. Right over here, there's one for Sodus Bay watershed. Why do they do that? Well, every, you know, snowblower and four wheeler and every little piece of equipment that people have outside, or people that are really irresponsible and just drain oils in different places, or any pesticides, fertilizers, all of that, those all become kind of everybody's problem when you look at things from a watershed perspective. How many cars are leaking oil in this teal space, right? That's all flowing through the Oswego River downtown. Um, so it's worth considering. It also opens up bigger issues. This here we go. Whoop. So yeah, here we go with me riffing and coming up with things on the spot, right? Um, Going back to our notes here, this line right here, and Tully, New York, just happens to be at that spot. South of there, water flows south. North of there, water flows north. But that water that flows south, consider everything that's going on in that whole area, actually flows all the way down to the Chesapeake Bay. They've had problems here, a variety of problems for a variety of reasons, with the watershed, with a chicken farm runoff is one of the big ones. And it turns into like, how do you legislate or try to get people to change when the water quality, the fisheries, the oyster bays, things like that are affected by what farmers in upstate New York are doing? You know, it goes all the way to like Cooperstown and Tully and all of that, all drains down into that. So these problems are not super easy to deal with. And that's why we want to raise awareness of what a watershed is. All right. Typically, let's go back to just like the geology of rivers. Typically, this would be the profile of kind of an idealized stream. This is snipped out of the year chapter 14. That higher in the drainage basin, the hills tend to be steeper, and as you go lower, 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 it tends to flatten out. That's going to have some effects that we're going to have to come back to when we get down here. But so keep that in mind. Higher in the drainage basin, in other words, up towards the headwaters where the water starts to gather, it tends to be steeper. This isn't a hard rule. It doesn't have to be this way. But then as it gets lower and lower and lower, it tends to flatten out. One important term I want to throw out there, it is in the book, I don't know if I put it anywhere else in these notes, is the elevation of the body of water that the river flows into is called the base level. So in terms of like, think about this in terms of potential energy, water that's up high is going to have the most potential energy and therefore eventually flow the fastest when it's in these steep parts and be capable of the most erosion downward. Whereas when you get closer and closer and closer to the base level, which again would be like, let's pretend that this is the body of water that this flows into over here, there's not as much. So there's not going to be as much potential for downcutting into the earth as there is higher up. So higher up, you tend to get faster, straighter streams that are doing a lot of erosion down. When we get down low, they tend to slow down, and we'll look at what happens there with meanders. All right. This diagram, I don't know, we're not going to label a ton of this, but I've had this help people in the past, so I'm going to do it fast too. Usually I take my time on this, but nobody wants to sit here watching this, right? So I'm going to trace this line right here, right up to the peak, and then right down the back of it right here. What that line, so the inside then, we're saying that's where water, any drop of water that lands or snow that melts, enters this river system, whereas anything on the other side enters another. So the inside of that would be what we're calling a watershed or drainage basin. That physical area of land drained by the stream, whatever you want to call it. So then the line, I'll write it down here. The line that separates two drainage basins is called a drainage divide. Separating out water that flows from this side to water that flows to this side. And again, they exist on different scales. Locally, if you're just doing like a day trip driving around a little bit, you might see these on different scales, but you're probably all, if you're up here, going to be in the drainage basin that leads to Lake Ontario, right? You have to go all the way down to the past the southern end of the Finger Lakes or past Tully to get to the next drainage basin that way. But you could still be in separate small drainage basins, small drainage divides, like between what is here in Sterling and what is over at Sodus Bay and then what is up there at Oswego. All those little tiny streams are also going to have drainage divides in between them. And then so you can like scale back to the largest and largest of those. In fact, I'll go find another picture. If we really zoom out and go to the grandest version of what a drainage divide could be, it's the Continental Divide. So this is in Colorado, but a day trip we took, and if you stood at this right here and threw some water that way or waited for the snow to melt, that's going to go down eastward, heading towards what would eventually get down into the Gulf of Mexico. Whereas if in this picture, if I turn around and face back this way behind the camera and chuck some water, that's going to make it down to the Pacific Ocean. The Continental Divide is a drainage divide, but just kind of the grandest version of it that separates eastward flowing water from westward flowing water, or if you want to look at it this way, Atlantic water from Pacific water. Smaller scale, yes, like this, and then smaller and smaller and smaller. And also on here, sometimes I talk about the water cycle, but we did that back in the weathering thing. Let's consider that this is all a function of the water cycle and that the rivers are the way to get that water back. And with it, it carries all of the sediments and dissolved materials that it picks up along the way. All right, which is what this chart shows us. I think we've already taken a look at this, but let's pop it up again to get to this golden rule of sediments in streams. This black line defines the relationship between stream velocity, how fast must the water be going, to particle diameter, how big of a particle can it move at that speed. So if you picture a really gently flowing brook, that's not going to be able to move a rock, the size of this thing. But if you take a fire hose and blare it on that thing, then yeah, you're going to be able to knock it down the way, right? The faster water goes, the bigger the particles that it can carry. So what that leads to, if you can like wrap your head around that a little bit, is that whenever water speeds up for whatever reason, and this is going to be our golden rule, when water speeds up, you get erosion. It can carry bigger particles, and it can and it will carry bigger particles, carry more particles, so it's going to move them downstream. That's what erosion is. All right, so let's say it's going arbitrarily the speed, it's going 1. If it's going 1 centimeter per second, that's a terrible line, but you get the point. Um, it could carry sand of that size, right? If it speeds up to 100, goes down a steep hill or something, now it can still carry the sand, the silt, and the clay, but now it's also going to be able to carry pebbles and the coarser sands. That's what erosion is those things getting picked up and taken away, right? The opposite case is what happens if water slows down. What you're going to get is that it could carry particles of some size. Let's say it was our water going 1 again. It could carry sand, but if it slows down to 0.1, it can't carry that sand anymore. So the only thing for the sand, the only thing that can happen is that it settles down to the bottom of the stream. It can't be pushed along anymore. It drops out. And that's what we call deposition. That rule right there, the rest of this stuff is really like an application of that rule over and over again in different ways. That's the key. That will certainly show up in the test in one way or another. So what we'll look at then, this is out of the textbook, is as the stream's flowing, where might the water be going faster and where might it be going slower? So here at A, across A, where the stream is straight, your fastest flow tends to be towards the middle, just a tiny bit below the surface. You get drag, resistance essentially, with the stream bottom, and the interaction with the air can slow it down a little bit as well. So just below the bottom towards the middle. But B, I don't know why they flip-flop these, but they did. At B, what happens on a bend is that the fastest water tends to go towards the outside. And that might not be a terrible idea to note that. So following our golden rule then, what are we going to expect to see? If water speeds up, is going faster, there's going to be erosion. So what we would expect to see is that it eats into the land over here and may migrate that way slowly through time. Let's write all that stuff down. Fastest, so there's erosion. You get the landform you get, and I'm going to find a couple on Google Earth here. They'll call this a cut bank. And we'll look for evidence on the outsides of streams from satellite view and Google Earth of that happening. All the opposite on the inside. On the inside of the curve, and they drew a little sandbar here. On the inside of the curve, the water slows down. So again, back to our golden rule. When water slows down, there's deposition. Let's go there. Slowest, therefore deposition. Particles that were in the water going a certain speed, when it slows down, can't be carried anymore and get dropped off. They tend to call these point bars. All right, so we'll find some in Google Earth. But before we jump too far, let's just go back to this and keep in mind, this curving thing tends not to happen up here. The water's going fast. When water's on a hill, it's not going to take its time doing curves. It just gets down that hill. The steeper the river is, the straighter it's going to be. When you get down to where it's flat, that's where it's going to start to do these turns back and forth, or meanders as we call them. I guess, it's written all over here, but I can check that word up here if you want. Meander. These things, through time, develop all these curvy patterns. Let's check it out in Google Earth. Sorry. There we we go. Sorry, dual monitors are acting weird. Okay. Let's go down here and find a couple. I mean, you can see the boundaries of the states are defined by these things. They're all over the place. So here's an example of one where there would have been a bend, and it would have gotten really large, and then come all the way up around, and then pop down through over there. But what happens through time is that as these like get to be a bigger and bigger and bigger meander, eventually they're going to connect. And when they connect, water takes the shortcut, and it leaves behind this extra feature over here, which we call an oxbow lake. These two diagrams are essentially showing the same thing, but I don't know, maybe some people like one versus the other, so I threw them both on there. Okay, the bend gets bigger, the bend gets bigger, the bend gets bigger, but here it's getting bigger that way, here it's getting bigger that way. The two are going to connect and leave behind an oxbow lake. And yes, eventually they can get cut off, get kind of swampy, and eventually a scar. And if we look at Google Earth, you can see that all over the place. See all these like scars. And even within this area here, you can see the various paths of the river through time as this changed and changed and changed and changed. All right, what else? There's some good over here. This is a good example of outside cut bank, inside point bar. Look at what you see here. This is all sand. So sand that gets dropped off by deposition because the water goes a little slower. If we really zoom in over here, you see trees in the water. So trees at one point would have been on land, happily digging into their sediment with their roots, right? Existing. But as the outside of that erodes and erodes and erodes and erodes, the trees fall in. I've got a quiz question that will look just like that. So keep an eye out for that. All right, did we find other oxbows? Oxbows, meander scars, oxbow. Let's actually go closer to home a little bit too. Chittenango, yeah, right here. Chittenango Creek is a pretty good example of both. So Cazenovia Lake here, Cazenovia Lake in town. It's a little flat here, so there is a few meanders. But once you get from here to here, over that distance, it's really steep. This is a beautiful drive if you ever have the time. And the river, if we can find it, it's deep in this valley. It has a few bends, but eventually when it gets over here, there's a big waterfall, very nice. And then it's pretty steep, and you can see that the path of the river is much straighter. I'm going to give you a term for this straightness in just a moment, or curviness, whatever you want to call it. When you get down here to town, to Chittenango, this line right here, south of there is very hilly, north of there is very flat. So once we get very flat, you're going to see what happens to the stream. This is the end of it. I'm going right to the end. See how it like winds all over? Very curvy. Lots of, and there's little oxbows, there's meander scars if you look really carefully. Lots of big bends. And again, it being flat is the key part of that. So the term I have for that is sinuosity. I mean, measure of this is not a good scientific sounding definition, but I'd rather have it make sense to you. Curvy a river is. What you do is you take the straight line distance, and then you take the distance along it, and you divide them. So if it were a very straight stream, I'll start down here with a very curvy stream. If it's a very curvy stream, and I were to say, what's the distance from here to here? About 1.29 miles. If I then measure the distance along that, it's going to be a much longer distance because it's a very curvy stream. So when you divide those, it'll be far away from one. Whereas if it's very straight stream, like we get down here, if I were to measure the distance from here to here, and then the path of the stream from here to here, those numbers are going to be a lot closer together. Therefore, it'll be closer to 1. Like if you divide any number by a number close to it. If you divide 50 by 50, it's 1, right? 51 by 50 is going to be pretty close to 1. The closer you are to 1, the straighter the stream is. That's sinuosity. That measures how curvy it is. And the relationship then is you get a higher sinuosity on flatter ground. Because again, when it's steep, the water's just going. That's it. All right, we brought up a similar diagram in the last note set, but remember, rivers, not just water, it's also flowing sediment. And all obeying this relationship right here for how fast it's going to go and how much can be carried. Some will bounce along the bottom, some will be suspended. That means basically, I don't want to say floating because it's not the right word, but held up by the stream currents. Kind of feels like floating. There's also going to be some in solution. Remember, we talked about caves back in weathering, how certain minerals are soluble. If it's soluble, I think I said this back there, but let's mention it again. Oh, I got to pause. Sorry about that. If it's soluble, it can dissolve in water. Think of it with Kool-Aid. If you've ever made Kool-Aid, you put the sugar into the water, you stir it up, and it dissolves. Sugar is soluble. If you drink that, you know it's not water. It still has the sugar in it. It's a sugar solution. Kool-Aid should say sugar solution with some red dye in it or whatever color dye, right? Geologically, same thing. You've got water that flows over something that's soluble, like limestone is a great example. The limestone doesn't just cease to exist and disappear. It goes into solution and then flows, and then eventually somewhere else may reform. Yeah, what do you think? So the last little bit then of this, we'll do more, but the last little bit of this is what about deltas? Well, when a river meets the larger body of water that it flows into, it slows down. So when it slows down, it's going to drop its sediments, and that is what forms a delta. Now, there's some different kinds. I doubt I'll get into the nitty gritty on defining the different kinds, but understanding that it's again, it's like another application of this same golden rule. Because when water gets to where it's going and it goes out into that body of water and it's not constricted to a stream channel on a slope anymore, it slows. And when it slows, it drops its sediments. So that gives you what a delta is. There's the Louisiana one, a bird's foot delta, it's called. The Nile, very typical, like triangle shape. The Greek letter delta is where they get the name for this. They tend to be really fertile areas. River sediment with all the life that's happening in it, dying, decaying, all of that organic material tends to give you very fertile environments. We'll have to think about that when we look at flooding in the next video a little bit. But we can call that good for now with what a delta is. Let me look through 14 quick, like I usually do, to make sure we didn't skip anything too big. I think we're feeling good here, though. This is the more complicated looking version of this guy right here, if you're wondering what that is. But I kind of like it because, and I think I showed this in the last video, because it shows more with the idea that, hey, when water speeds up, that gives you erosion, and when it slows down, you get deposition. Yeah, we'll call it good there. Thanks, everybody. We will see you soon.